because of the lattice points that you have. So it's like what you have in the crystal lattice too. There's always a cut-off band gap. Wafers above a certain frequency cannot propagate across the crystal lattice for that reason. I think that's the case. Okay, you can think about it. But that's a good question. Let me see. I have 5 minutes left. Let me tell you something about the E algorithm. E algorithm is very popular. Even after so many years of invention, I think it was invented around 1966 or something. And even after that many years, people are still using that. Because it's simple, it's robust. It actually captures the physics quite well. Okay, it's very easy to implement. And physicists actually pick this algorithm up, and if you go to visit the website of MIT or Stanford, and the physics department is there, you got this program for free. Okay, and they just love this program, this kind of algorithm. So how does this algorithm work? Essentially, if you start with Maxwell's equation, curl of E is equal to minus dB dt. If I just take one component of this equation, say the x component, I will have an equation that looks something like this. Okay? And how do I implement this? In a nice fashion, and E, Mr. E, Ken E is his full name, actually came up with this very nice idea that he did define and design a grid that looks something like this, that we staggers the E and the H field. Because if you look at Maxwell's equation, curl of E equals to minus dB dt, curl of H equals to d dt. What is actually happening here is that you can think of B curling around E, E curling around H and E curls around each other. And then they curl around each other to get wave propagation. So he defined a grid that looks something like this. That say this is the M and P point. The E field would be defined on a grid that looks something like this. And then the E field, this is the E field would be defined on this grid. Okay? And then there will be some hidden grid at the back I won't bother to draw. Okay? And then the H field are being curled around by the E field. So the H fields will have something like face center cubic kind of lattice. The H field will go something like this. This will be an H field. And then it will be an H field. So this is E, this is H. Okay? And if you are imaginative enough, you can think of the H field as being curling around the E field as well. You extend yourself. Okay, and think of another grid. There are two grids here, two staggered grids. Okay. Two staggered grids. One that the H field lives on, the other one that the E field lives on. They actually staggered with respect to each other, and the two grids curl around each other. And he puts the H field on one of the two grids, and then the E field on one of the two grids. And then you start writing down the finite difference equation for this. And then if you write down the finite difference equation for that particular example, then you can write it in this manner. dx m plus half p plus half. If I call this an MNP point, okay, this is my hx, this is my x-axis, this is my y-axis, this is my z-axis. Okay, this is hx. Hx will be given by the half grid point. Okay, this is half in the y direction and half in the z direction is what it means. Half in the y and half in the z direction. Okay, this thing has two different time steps. The two time steps are L plus half minus the same field at L minus half. Okay, So you take this field over two different time steps, and you take the time steps in such a manner so that one is half a step forward in time, the other one is half a step backward in time. And then you start to write down the right-hand side. The right-hand side is just the ex dy. The ex dy will be equal to, let me see, sorry. This is wrong, right? This equation is wrong. It should be z, right? Z. Z. Okay, that should be z, right? So the EZ dy, EZ is pointing upward. So the z dy is in this direction, difference between these two. Okay, write down the difference between the two. You will get E, Y, M. So you change in the Y direction. So it's n plus half, P plus 1. P plus 1 because this is at the half. Let me see. Y, this is EY. EY is this one over here. This one over here. So the difference between these two. So this is n plus half. So y is in the half direction, p is in the one direction. P is this one minus E y m n plus half p. Okay. So this is p plus 1, this is p plus 1, this is p. Okay, and then this is n plus half 1. Okay? And then this will be in the L time step. This is the approximation you can write for this first derivative. And then you can write the second one. The second one will be the difference between these two. Okay, the difference between these two. And you can write it as 1 over delta y EZ m n plus 1 p plus half L minus EZ m n p plus half L. Okay, this is m plus 1. This is n, right? N is y. This is n plus 1. This is n. This is p plus half. P plus half. And then there's a second difference. You will take out the two fields. Okay? So you put the field on two staggered grids and keep writing Maxwell's equation on the 6 faces of this cube. Actually, just 3 faces, not 6 faces. 3 components of this cube. And then you can time step all the 3 components of this Maxwell's equation. And then you do the same thing for the L10 equation, 3 components. And then you can do marching forward in time. And this algorithm is very nice in the sense that it captures the physics of EM waves very well. It captures the physics of EM wave, and there's no low frequency breakdown. You can run this at very long time steps. If you satisfy the stability criteria, you can run it for infinite time, and there's no breakdown. Running the code for infinite time is like trying to pick up the low frequency component of the signal. In order to pick up the DC component of the signal, you have to run the code for infinite time. So you keep time margin for infinite time, and still no breakdown, which means that it does not have a low frequency breakdown. There's no DC breakdown. Whereas if you do finite element method and some other fancy numerical methods, it's very often that you run the code after a certain time, it breaks down. When it breaks down after a certain time, it means that it's not low frequency stable. It has some low frequency modes that creeps up and makes the code unstable. Okay? Are there any questions regarding E algorithm? It's a very nice algorithm. You can actually write it in an afternoon. Write the code and then play around with it. And then give out the code for free. I have some free codes to give out too if you want some of that. Okay.